Okay, so I think we can start. So welcome everybody out there on the internet and the MIT students. So today's lecture is entitled Our First Climate Model. And maybe the first thing I can say is that this lecture was inspired by a wonderful lecture by Henri Drake, who's a PhD student over in EAPS, the Earth and Atmosphere Planetary Science Department over at MIT. And I think it's a pretty fun lecture. So let's see. Uh, I'm going to do the lecture slightly differently from Henri's. In fact, if you ever want to go and see Henri's original video or the original notebooks, I've put links to them. But what I decided is to start off in kind of, I wanted to talk about what I see as computational thinking, where we use the computer to kind of understand the math as opposed to the other way around. So I'm going to start like a little bit like a differential equations course, except doing it the way you would do it with a computer, as opposed to how many traditional differential equations courses would go. And I'll only slightly mention the climate at first, and then I'm actually going to go and delve right into the climate model. So I really believe, and I've mentioned this in previous lectures, that learning about a little bit about how these climate models go is important for everybody on the Earth these days. I think it's not just for people who are going to specialize in climate models. Of course, we're going to do a simplified model. This is going to be like one of the first models that was ever invented, but it's already quite illuminating. And so I really think that this is something for everybody. All right, so let me begin. The first part is basically going to be differential equations. So just to begin, I'm going to start by talking about a function of time t. So I'm going to begin by calling it y. Later, I'm going to be interested in the temperature of the Earth. But for starters, I'm just going to call this y of t. We'll start at t equals 0, and the value of y at t equals 0, we'll just call it y0. And I'll write y prime for dy dt as is typical. Now, if this was an ordinary differential equations class, we would start simple. We would say, for example, consider y prime equals a constant, like a, and then you would solve it exactly symbolically. Your professor might put it on the board, or your textbook would have the solution, or you'd be asked to do this for homework. And you would find, okay, the solution is y of t is at plus y0. And you can check, oh, let's see, at t equals 0, you've got the right value. And if you take the derivative, look, the derivative is a. Okay, good.
Could
And
you
then,
zoom in a bit, please?
absolutely.
Thanks.
Okay,
Yeah,
there we go.
thanks.
All right. So now, and then once you've mastered this very simple equation, you can go on to get a little fancy. You can add another term. So again, this is how a old-fashioned differential equations course might go. Not really what I'm advocating, though there's something to be said for doing it this way. Uh, but I think the computer really helps in other ways. So let me add in, let's make this linear. And for reasons you'll see later, I'm going to choose to make this minus by. So now I have two parameters. Before I had just the parameter a, but if I have the equation y prime equals a minus by, you can get this symbolic expression for the exact answer. I mean, you can quickly check, for example, that at t equals 0, this is 1 minus 1, and you still get the y0. You can differentiate it if you like. In a way, this is sort of how classical mathematics, simple nuts and bolts mathematics might go. You would check, you would start investigating this. You would see that as long as b is not 0, we can actually let t go to infinity, and all the exponentials disappear. And you see there, it heads towards this constant a over b. A little bit more clever is just to set y prime equals 0. That's an equilibrium. And y prime equals 0 is exactly at a over b, right? When you put in y equals a over b, this is 0. So, you investigate this sort of thing and you get an equilibrium. But this is like very symbolic math. There aren't that many pictures. And it doesn't, you can only take it so far. I mean, simple functions you can do this with, but still it's just, symbolic math. I don't know. I think it doesn't really convey the story. Though it has all the information content, it doesn't quite do it the way I like to see it, which is visually. But let me keep going. We have a, We have a minus by. Now let's add in a function of t. So I'm adding one more term, right? Sometimes this is called a forcing term. We'll label it f. And the symbolic solution, the analytic solution, I don't even know. I've heard people call this analytic, but to me, when you have an integral, I'm not even sure if it's analytic anymore, but maybe that's a matter of debate, whether to call this an analytic solution. But in any event, this gets even harder to sort of follow, really. I mean, but this is an exact solution in case you care to see it. But none of this excites me, none of these exact solutions. But as long as I'm going to give you a preview of where I'm heading with this, and just kind of listen to this now, and I promise in the second half of this lecture you'll see it. This is a model of a sun heating the earth and none of the heat ever escapes. This is a model of the sun is heating an earth and the earth sends some of the heat back into space. Okay, and this is a model of it's this one, the sun's heating the earth sends heat back into space, and we have a greenhouse effect that's forcing higher temperatures. So I'm going to sort of systematically revisit each of these three equations in a climate model. But for starters, let's just do the math. Let's just look at these equations. And so now I said this is how I prefer not to see it so much. Again, not that it's so bad and it's useful, but I like to take a look at these things I like to see the numerical solutions. I like to see the plots. So, stuff like, I'm gonna systematically show you the solution to those three equations, the ones with increased complexity on this graph. And so let me just remind you that Dave's already done this a couple of times, but Julia's got an incredible set of ODE solvers written by Chris Rakakis. It's probably the best set of ODE solvers in the world. And all you have to do is, if you want y prime equals f of y in Julia, you define this function f, and this function is typically written as a function of y, parameters p, and time t. And then you call Julia's ODE problem, where you give the initial condition, the time you want it over, and the parameters, if any. And then you use the Julia command solve, and then you can do whatever you want with it. I like to plot it, so that's why I'm putting in plot. Okay, and so let's see. So here I've sort of put together the entire the entire complicated function, if you will. But when b is 0 and force, let's see. Let's go slowly. Let's look at the picture. I'll get back to the. Let's look at the picture for starters. So for starters, everything is basically 0. And let's see if we can make it a little smaller so you can see the picture. Okay, I'm gonna here's the function. Let's do nothing but increase a. Okay, so here, let's maybe like that. So a, just putting in a, y prime equals a constant. Of course, the solution is going to be linear, right? Everybody knows how to integrate a. I can move the y0 lets me move the initial condition up and down. So that just kind of moves things vertically. If I, oh, you know what? Before I do anything at all, though, let's go back to the beginning. Let's look at the direction fields. Let's remember that a differential equation means nothing other than starting at the left and following these direction fields wherever they might take you. Okay, that is what we mean by solving a differential equation, basically, right? So you're going to just follow the direction every time. It's like you're doing a treasure hunt, and when you get here, the note tells you where to go next, right? So the direction field tells you where to go next. Okay, that's what we mean by solving a differential equation. And of course, in the old days, it just meant writing down a symbolic solution, but that's what it really means. And I'd like to point out that in the initial state, all of the direction fields are constant. They're actually horizontal. Even when I move A, oh, I've got that little bug again. That's annoying. Hold on. Let's see if we can get this to move now. Dave, you ever figure out why this happens?
No. Maybe if you scroll down a bit. Does that help?
Oh, it did help. That's the solution. Scroll. Oh, I need to scroll down a little.
Fon said he had fixed it, but I don't know.
All right, but here, let me go ahead and change A only, And I'll point out that again, if you look at all these yellow lines, they're all pointing, I don't know, northeast, I would say, right? But the point is that the yellow lines do not depend on your T or your Y, right? They're at every position, it just says move northeast. So basically it takes a straight line and it keeps you in a straight line. When I add B, a little bit of B, let's do that. So let's add a little bit of B. You can see that you'll notice, well, of course, B is only multiplying Y. And so if you go across a row, you might notice that, again, the direction field is constant in any one row, right, for any constant Y. Obviously, if you go along a column, things are changing. So what that tells you is that where you're going is going to be a function of your Y value. Ultimately, this Y value is going to be temperature. But it doesn't depend on what time you're doing it. Okay, and it doesn't matter. I can make the initial condition go up and down, but you see, because I have no forcing function of t, this c is 0. It goes just in that way. On the other hand, let me put in the forcing function. The forcing function that I'm going to use is nothing other than c times t. Okay, so it's just this linear function with the constant c. So if I make b 0, oh, Phil, what do you have to say? If I put a c in, right, you'll see now that these things will only depend on t. If you look in a column, this is sort of the backwards way. If you look in a column, then the vector fields are constant, but if you look along a row, they're obviously changing. Okay, so in summary, A doesn't change. A is the same everywhere. B influences you in the y direction. C influences you in the time direction. Okay, so now let's go and look at the solutions. Again, we have the symbolic solution, and you can get everything I'm going to say from there. But I think that this is really computational thinking, playing with these sliders to the point where you really understand what's going on. What are these equations really doing? So when B is 0 and C is 0, as you see, this is just a line. If I start tweaking B a little bit, you'll see though that the thing that was going to infinity is all of a sudden reaching an equilibrium, which I'm drawing in the white line. It's reaching that B over A equilibrium. You see, so I mean, I can move it in different places, but adding a little bit of B is somehow holding it. You can see it. This is going to go over here. That the B is what forces the fact that it's minus, by the way, and it's a minus a positive number is helping. It's forcing the time evolution to reach an equilibrium and not go crazy, not go to infinity. So we're going to see that this has something to do with how the Earth tries to heal itself, right? It tries to reach an equilibrium. And so when we do the climate model, this is the sort of thing that kind of explains what's going on, right? It's just this very simple term, the By, is doing that. If B was 0, again, it goes off to infinity. If B is something else, it'll reach an equilibrium, right? A tries to push the equilibrium higher, but it will still reach equilibrium if I make it. Okay, so, and this is what I would encourage when I'm talking about computational thinking for understanding differential equations. I'm thinking that this is the sort of thing that everybody should do when they encounter a differential equation. They should think about the direction field, think about the lines following the direction field, right? And maybe more than thinking, actually plot these things and understand the role that every piece is playing. And I've always felt that the symbolic solutions kind of hide this a little bit. I mean, it's there. We all know it's there. And if you look at it closely, you see that it's there. But nothing like a picture being worth 1,000 symbols, if you ask me. Okay, and now let's go and look at what happens with the C part of it all. Now you see the C, the forcing function, is actually messing with the equilibrium. So if I add a little bit of this forcing term, I'm going to add it again, you'll see it actually pushes it. The more of the forcing function I add, the higher it pushes up the Y value. Ultimately, it's going to be a temperature. You see? So we could change this function to a slower growing function like square root of t, right? And you've got the power to change this yourself. And this will just let this sort of work its way through. And you see it kind of, it slows down the impact, but in the end, the impact is still there. Okay, so you can force this function with any function you like. I'll return it back to CT just for next time I use this notebook. But you see that this is basically, this is basically a simple differential equation. For complicated forcing functions, there's no way it could be solved analytically. But yeah, you absolutely can understand this. I mean, I haven't even tried some funny functions. Maybe I'll try it now just to see what would happen. I have no idea what would happen if you did sine t, but it should make it go up and down since it oscillates. And there it goes. We can see it doing its thing. Kind of fun. Yeah, there you go. Oh, look at that. That's
But that seems to actually be converging to the equilibrium again, maybe.
Oh, you think it is? It's possible.
Oh, no, actually.
I wouldn't know.
I guess not. No, it's going to oscillate around the equilibrium.
Yeah, I would almost have to let it go for a longer time. Should we do that? We could do that. If I could find it here. Here's where I'm going to 10. You want me to go 10 times as far and just to see what happens? Oh, look at that. Oh, it is going towards the equilibrium. You were right. So I guess because on average, sine of t doesn't grow.
Yeah.
Oh, that's pretty fun. Okay. You want to try one more function before I move on? Any fun functions? I do log of 1 plus 2. They'll just slowly increase, but maybe not very fast. This one would like to be, at c equals 0, of course, it still goes to the equilibrium, but not after that. Yeah, because it's not oscillating. All right, so anyway, this is the sort of thing you can do. And pretty quickly, you could exceed the abilities of any classical mathematics, I would imagine, just being able to draw this picture. Okay, let's go back. Also, I just want to restore things in case I ever use this notebook again. So I'll go back to time equals 10. All right, good. So now I'm going to start talking about climate science. And basically, if you do go back and look at Henri's lecture from last fall, this is basically where the lecture started. So I thought I would kind of pull out the differential equations first, because I think it's kind of easier to now that you see what the math is doing, I thought it would be good to sort of separate that out, and so we can now talk about what the physics is doing. In a way, it's kind of funny. Whenever I see a physical model, I kind of wish everybody would do what I just did, because there's always like the simple math, and then there's like a million parameters and variables, and you kind of get lost in the confusion of them all. But of course, that's sort of the nature of physical models. And in the old days, people tried their best to come up with all of the parameters. And a fact of life these days is that there are parameters we know and there are parameters we don't know, but we fit. We have data and we fit those parameters based on the data. And in the old days, of course, it was linear fits and polynomial fits. Nowadays, people fit with a neural network. But I'll talk about that a little bit more later. Let me talk about the simple, this is sometimes called the zero-dimensional model, or the energy balance model of the Earth. Zero-dimensional model means that we just think of the Earth as one point, like the average temperature. There's no difference between, Boston and, the Middle East or something, right? There's just, it's all been averaged out. Okay, so basically, like the three kind of increasingly complicated differential equations that I showed you, there are going to be three effects that we will concentrate on. One is simply the absorbed solar radiation, the energy that comes directly from the sun's rays. So that will actually increase heat, right? We're getting heat from the sun. To balance that out, there's going to be outgoing thermal radiation, and that's basically the heat that's on the Earth sort of escaping back to space. It's not staying with us on Earth. Okay, and then there's what's causing all the trouble these days, the human-caused greenhouse effects, the the trapped outgoing radiation, because we have carbon dioxide and methane and lots of other things that are causing trouble up in the atmosphere. And so this third term obviously didn't exist until the Industrial Revolution, when we started polluting our atmosphere, but it's very much a real term right now. So here's a little picture that kind of shows roughly what's going on. So here's this happy sun heating the Earth, so we get our incoming solar radiation. And here's the outgoing. Before there was carbon dioxide, this thermal radiation would just go completely outward. That's the blue. You'll see this is all color coded very nicely. The yellow the yellow is this orangey yellow, this blue, and then there's of course now there's the carbon dioxide, which is the greenhouse effect. And the oceans kind of try their best to kind of equilibrate everything that's going on. The oceans, for example, absorb a great deal of the heat. So, and we'll try to model that in whatever way we possibly can. All right, so let's start with, the first one is the easiest. It's the easiest thing to model, and we know everything about it. The incoming absorbed solar radiation. Okay, so this is going to be another example of temperature prime equals constant. So, so here's a few numbers that are going to sort of end up being in the constants or in the time, but we'll say that the Industrial Revolution started in 1850. That's kind of roughly the decade that we generally use in climate models. The average temperature in 1850 has been measured. It's taken as 14 degrees Celsius. There's the power that comes from the sun, which, I'm just taking these numbers from Henri, but it's listed as 1368 watts per meter squared. And the planetary reflectivity is 0.3, and the upper ocean heat capacity is 51 joules per meter squared per degree Celsius. So this is kind of where the physics gets not so much complicated, but the devil's in the details, as you might expect. But ultimately, what we're going to do is we're going to turn all these numbers into a simple differential equation, which is that the time dependence of temperature is going to be, the rate is going to be multiplied by the C, and it's going to be equal to S times 1 minus alpha over 4. And so it's going to be about 239.4. Okay, so let's just, before we explain this, let's just see what this would look like if we literally could heat the Earth nonstop and never let any bit of the heat back out, or then if we started at 1850 at 0 degrees Celsius, we would already be at a burning 800 degrees Celsius on Earth. I mean, this would just be something that no human, no life could be able to withstand. So it's good that we don't just take energy from the sun and keep it on the Earth. Okay, but that would be the linear. And just to kind of talk a little bit about some of these constants and how it really works. So I'm going to try to explain where all of these parameters come from. So let's see. So let me start with the power of the sun, and that's 1368. And it turns out that we reflect some of that right away, right? So that just gets reflected from the Earth immediately. And the reflectivity constant, I'm told, is that we can use is 0.3. And so literally S times 1 minus alpha is the amount of energy from the sun that isn't reflected immediately. And then there's this cute little picture that tells you, if you think about the entire area of the Earth, if you think of it as a sphere, the surface area of a sphere of radius r is 4 pi r squared. But we only get sun through half the Earth on a day. So you only like half the planet gets lit. And it's only the normal component of the energy that we actually manage to take in. And so if you think about having sort of a flat disk, that's area pi r squared. And so literally we only take in 1/4 of this energy to spread around the Earth. And so this is where the divide by 4 comes in. Okay, so I think there's a clever little picture to talk about sort of averaging the sun's rays that are coming in every which way, but just to take the normal component as it comes in. So S is coming from the sun. We reflect back alpha S, divide by 4 because of this geometry, and that's going to be the official absorbed solar radiation. So I guess I can remove the semicolon, and you can see that this is going to be that number that we have, 239.4. Okay, and then there's this C number, which I'll say a few more words about, but this has to do with the ability of the oceans to basically kind of ameliorate a certain amount of the heat. Okay, and then I also have the pre-industrial temperature of 14, and I can solve the ODE problem, and we let me just see, yeah, and we solve the ODE problem, and that's why that's how I managed to get this linear graph. Just a few more words about C. Okay, so yeah, so this is the key part of the sentence, that the heat is closely coupled with that of the ocean, upper ocean, which has this is the C equals 51. I could put it back in. The capacity of C equals, it's this right here. Let's take it out of here and put it here. There we go. Okay. And basically, this is shielding the heat from the Earth. That's the way I look at it. Okay. So anybody have any questions about the, let me take a look if there's anything in the chat. I guess not. But this is sort of the first simple model of the sun baking the Earth with no heat coming out. Okay, so now let's go to the outgoing thermal radiation. Okay, and this one, I'll warn you in advance, is a little bit kind of more hand waving. So in two particular ways. So of course there are more complicated models, but we're going to just give a basic, very simple model. Okay, so the outgoing thermal radiation is has to do with it's actually a combination of the black body radiation of the Earth radiating its heat out into space. There's also a little bit of so that would actually cool the Earth. There's a little bit of warming that goes to sort of water vapor feedback, and again, I'm following Henri's lecture here and accepting the fact that these physics are very complicated to deal with. So why don't we just come up with a linear model? Okay, so the outgoing thermal radiation is going to be a linear function of temperature. So this is where that second model comes in. Just to remind you, y prime equals linear in y is kind of what we're doing. We're revisiting the linear function in y. Okay, and so what can we do? So if I want to fit a linear function, I would have to find two parameters, right? Two points determine a line. So I would have to fit two parameters. But what we're really going to do is we're going to fit one parameter intelligently, and then one's going to come out of the air. So we could make the argument that the pre-industrial temperature was an equilibrium temperature. You see, we actually remember from earlier in this lecture, I pointed out, I'll go back to show you, I pointed out that there's an equilibrium at A over B, right? And so if I actually know an equilibrium temperature, then I actually know the ratio of A to B. See, so there's a reason why I told this to you. I was planning ahead. Okay, so let's go back here. Since I know the equilibrium, I know the temperature just before the beginning of the Industrial Revolution, I can use that and say, that is going to be my equilibrium temperature. And so the ratio of the constant term to the temperature should, when I set this to equal 0, I should get the equilibrium temperature. And so I've managed to remove one variable. So now the only thing I have left, so now I'm going to say that the combined effect is going to be B times temperature of 0 minus temperature of T for some value of B. Okay, and the minus sign over here indicates it will restore equilibrium. And the value that people choose based on fitting data, we'll see a little bit of that later, is 1.3. Okay, so again, right now I'm taking this out of the air. Later, we'll see a little bit how you can actually get this by fitting a model. Uh, but meanwhile, let's go ahead and play with this. So now we're at the point of having the sun coming in and the outgoing radiation, but no humans to pollute. And you can see that even if you fiddle with the start temperature, it's always going to reach the equilibrium of 14, which was the pre-industrial temperature. Okay, uh, so this is, I don't know. I think it's really neat to be able to see the Earth restoring its balance, even if you mess with some starting temperature. The Earth will restore it based on this model. Okay, we'll go right back to 14 degrees, assuming that there are no humans around to muck this whole story up. Okay, so that's exactly what's happening. And this picture is completely obtained by just setting up the ODE problem that, it's uh, it's just b times, it's this linear function right here. That's all it is. It's this linear function, and then we divide by c for the cooling of the ocean. Okay, and we'll just start wherever you want, and we'll go 170 years. That'll bring us right to 2020. Okay, so that would have been last year. I guess if you want 2021, I could have gone 171, but you wouldn't see much difference. Okay, that would bring us to 2021. Okay, so to recap, we have a pre-industrial Earth over here, and the model just has any perturbations of initial temperature being restored by the Earth to go back to 14 degrees. So now, in this next piece of the model, we'll have the human-caused greenhouse effects. So we'll assume that something bad is happening because we're putting carbon dioxide into the air. Okay, and so this is going to put in the forcing function, that forcing term, and there's going to be two parts to this. One is going to be what actually, what is the badness of uh, of increasing the carbon dioxide, and the answer is this badness is going to happen on a log scale. Okay, and so this function is going to happen on a log scale. But notice there's no time in this. This is not a. We can't yet. We're gonna need something else. But let's. There's no time in this equation, right? It just says that the human-caused greenhouse effect is going to be some forcing coefficient times the log of the carbon dioxide now divided by the carbon dioxide that at the pre-industrial time. Okay, and in fact, how this is going to go is going to depend on the future of human behavior, right? We don't know what humans are going to do. We don't know whether people are going to stop putting carbon dioxide in the air, or they're going to increase it at a faster rate, right? And so this is something that we can model with any prediction you want, but this is a physical effect that is known. The time's not modeled in the above. It's just the human-caused greenhouse effect will be this. And again, more parameters that come from these folks who do this for a living. The forcing coefficient will be 5 watts per meter squared. That's the number they're going to use. So that'll be the multiple that gets used here. And the pre-industrial CO2 number is 280, right? And so now we're up, I think we're almost, is it 400 and something, 412? I forget what the number is now. But it's probably good to know these things. So yeah, what is the CO2 ppm today? Let's see if we can get that number somewhere. Yeah, it's about 400 in 2019, it says 410. I think it's more now. This is today's date. So 420, 417, if I'm reading this right. I think it's actually good to know these numbers to kind of memorize it. So we've gone from 280 to something like 417 or 420 today in terms of parts per million. Okay, so this is so it's that log ratio of that number today over the pre-industrial that's going to affect the greenhouse gas. So here's the function. I'll put it into Julia form. It looks just like it looks basically just like this equation here. And I'm just testing that the function works. So, okay, so let's see. So So this is just a graph of this function. It basically kind of shows you that uh, there's no time in this graph. It's just saying that here's CO2 in a bunch of different concentrations. Here you could see we're just doubling. We keep doubling. I mean, the present day looks like it's around here. It's in the 400s, right? And this was the pre-industrial. And so you can see, to what, if you call this zero, you could see to what extent we've increased the forcing function on carbon dioxide. Okay, and uh, I it's actually I've been playing with different time dependencies of carbon dioxide. Again, you could write your own. So here, let's start with the simplest, that it's a constant. There's no emissions. Carbon dioxide as a function of time is exactly what it was at the pre-industrial. And of course, what you're going to get then is what you'd expect. It'll go to this is temperature now. It'll go to the 14-degree equilibrium. Here's another model. This is basically a test model. It says that we are going to increase our carbon dioxide 1% a year, starting from the industrial times, the pre-industrial times, and you can see that takes us up to that. This is actually pretty serious because it adds something like 5 degrees. It looks like that's a lot for in terms of the Earth. Every degree of warming of the Earth, melts oceans and polar caps, and it just does lots of bad things to this planet. Okay, and another curve that I'd like to show you is the one that uh, people have been using to fit historical data, and that's this one. And you can see that uh, I can start. Maybe I'll start the. Where's the? I've got to find the start time. Where was it? Yeah, the start. Let's make this be the pre-industrial number at 14 approximately, and then you can see the Earth's temperature moving up over here. Maybe what I'll do is maybe I'll just plot it a little bit. Let's plot it a little bit more visibly. Yeah, so you can see this moving. This is fitting sort of the current. This is pretty close to the history of how the temperature has been going up on this planet. Okay, so yeah, so this is actually a repeat of the same picture. What is this? Oh, this is the carbon. Wait, let me just make sure I kind of did this in a funny order. Okay, yeah. I don't really need this picture. Let me tell you about um, so 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 how how good how good is this are these fits? Well, we've got real data, and there's this data that comes right from the Mauna Loa volcano in Hawaii. They do the readings over there, and if you go to this website, you can find out all about the readings. Um, I'm not quite sure why they put it there, though. I mean, if I had to take a guess, maybe I shouldn't speak without knowing, but if I had to take a guess, you'd think they'd probably want to know what's going on with the volcano anyway, in terms of carbon dioxide. So maybe they just have readings even when the volcano is not active. I'm not sure, but anyway, they have an observation center over there in Mauna Loa, and here you can see um, I'm grabbing the data, and I guess this is already Dave. Has this already appeared in the homework, or is this new Julia commands? These CSV.reads. Otherwise, I should have maybe listed them as new Julia commands.
I mean, I
We've
think
seen them already?
we've done CSV reading before. I think.
Okay, so then it's not new. But it's always good to be reminded how you can grab data off of a file. And so there, there's this file here. Let's just grab it and just open it up so we can actually see it. So this is this file. Oh, this file is not going to open on the browser. Never mind. It's being downloaded. But anyway, it would look something like this. Probably not formatted as nicely, but it would look something like this. So what we're going to do is download the data to my machine, read it into a Julia data frame. It's going to get the header information, year, month, date, carbon dioxide. Actually, it was in the fourth row of that file. If you could see that file, you would see it. And yeah, so that's where the header's coming in. And what is the data row equals 7 again? Oh, that's where we start the data reading from. Yeah, there's a bunch of skipping spaces like the 5th row, the 6th row, and the data starts at the 7th row. Okay, and so here's a picture. Here you could see some of the data, the first 11 rows, and data is in the 5th column, 1, 2, 3, 4, 5, the CO2 column. But as you could see, oh no, there's missing data, right? So these minus 99.99s are indicative of we didn't get a measurement that month, right? So this is being done starting in 1958. We get one data point every month, and we could take a look at a lot more data. Oh, what did I type first? I don't know what I just did. What did I do? Did I hit an R? Oh, where did that R come from? Yeah, so you could just see more of this sort of data. Did I mess something up? Is it okay? Let's see.
No, you messed something up, I think.
You know what? Why don't I just Control Z? Let's see, what have I done? Oh, data row equals 7.
Yeah.
Yeah, I don't know where that R came from. Okay, so Anyway, so this is actually worth talking about. What do you do when you get missing data? Well, the way I decided to deal with it is to actually only keep the data that's positive, and so I'll call this a valid rows mask. And eventually, what I'm going to do is only plot the data in the valid rows. And so this data,
It might just be worth saying exactly what's going on here. So
go for it. You want to say something?
So yeah, so just this mask, just you can see that it's just telling you for each line, for each row in the data, is that condition satisfied or not? That's giving you a vector, a special type called a bit vector, but it's basically just a vector of trues and falses. And then what we want to do is then, just take the rows that satisfy this condition. So just take the rows that correspond to the trues in that vector.
And that's happening with this indexing command right here.
Right.
So it's happening here. It's also happening here, right?
Yeah, that's just wanted to say that that's what we mean by a mask. And then exactly. So we're indexing using a vector, and so it'll actually extract. It realizes that it's a vector of booleans, trues or falses, and it will just extract the rows which satisfy the condition, which are true.
So literally what I'm doing is I'm grabbing as the first coordinate of my plot the date field where it's valid, and this is the CO2 field where it's valid, and you can see I'm labeling this as Mauna Loa CO2 data. And so this blue wavy data is a picture of what you just saw. That's this Keeling curve that's talking about the actual carbon dioxide levels that have been measured.
Okay? Which is quite scary if you think about it, actually.
It's very scary. But but again, you knew that it was hitting the 400s now, right? I mean, we know that it's, again, if I'm reading this properly, something like 417 or 420 today, right? So which is pretty much what you're seeing here. Okay, and the red curve is just a fit, and you could take your own fit. This is a cubic fit. It's that cubic fit that I used as one of my choices. I'll go back here. This is just a simple cubic, right? And this is the one that I'll use to fit that curve. And so if you wondered where did I get this, 220, whatever, this fits very nicely, this picture, right? I mean, I think many people would agree that this is a good fit of the carbon dioxide as a function of time. Okay, so we need some way of figuring out how much carbon dioxide is a function of time so that we can take the greenhouse of that. So now what I'm going to do is I've got some other data, which is the actual average temperature of the Earth, real measurements of the average temperature of the Earth. Okay, and so this data is these NASA observations, which also came from another file. I mean, I have it down at the bottom somewhere. Where did I do? Yeah, here they are. So these are the NASA observations of temperatures. I got that over here, but let me just go back to the picture. So these are the NASA observations, and this blue curve is just this differential equation solution. It's the same solution that you saw earlier. Okay, and so you see that, uh, I mean, what are we checking here? Just in case you've lost track, let me remind you, this doesn't have time. This is carbon dioxide. Uh, well, it does, this is carbon dioxide. It doesn't have temperature. This is carbon dioxide as a function of time. And um, we're asserting that there's a correlation between larger carbon dioxide and larger temperatures. And I think that these historical curves make it undeniable that that there's a correlation between the increase in carbon dioxide and the increasing temperatures. And further all, um, if you believe that this blue line is something of a good fit to the data, it's in some basic average trendy way, it's basically showing you by what mechanism the carbon dioxide is influencing the temperature, right? It's we have a nice exact, well, or it's not a bad fit of what's been going on. So now, of course, um, this is this is the past, but then there's the question of what will happen into the future. And oh, wait, before I do that, I'm sorry. There's one other thing I wanted to tell you. Uh, we could change this fit a little bit. You can play with it yourself. So you can change. Do you remember that B parameter, which is telling you to what extent the heat is reflecting back into space? And C was the effect of the oceans. And I pulled these numbers out of a hat. But what people really do is they fit data, some more complicated than this, but this is the sort of thing that people would do. They would play with these B's and C's parameters, not by hand, but probably with a minimization, least squares minimization operator, and they would try to possibly see if they can get a better fit to the data. And so this is how these things sort of happen. And then of course what we want to do is ask ourselves, what does this all mean for the future? And uh, there are these different models, and you can read about them if you want, where the low emissions one is that we at least managed to keep it below 500. Again, we're 400 and something today. And then the scary model, well, they're both scary, but the scarier model is the high emissions going to 1200. And so this red line shows what's going to happen to the carbon dioxide um, with the high emissions model. The blue says what happens if we lower our emissions. And this is at the carbon dioxide level. And then if you solve the differential equation, you get it at the temperature. And of course, the Paris agreements say that which the previous administration has pulled out of, and the current presidential administration's come back into, uh, says that we're going to try to stay no more than 2 degrees above the pre-industrial temperatures. And so it looks like we could do it if we can keep below the 500, but not if we let loose and go up to the 1200. So all of this stuff, have the ability to run these models by yourselves. Everything you need to know in terms of sort of a basic zeroth order model is all right here. There's a couple of other things that you might want to look at, like there's this nice little video about what's really warming the Earth. Uh, but basically, you see that understanding sort of at a high level, the basic mechanics of what goes into a climate model is really not so bad. It's all self-contained in one lecture on the behavior of very simple differential equations, which I recommend doing it with computational thinking approaches as opposed to the symbolic approaches, but whatever works for you. And then the rest is just feeding in parameters into these very, very same equations. Now, you might ask, why do people need high performance parallel computers that run a billion times faster than your laptop to solve climate models? Well, there's a lot of complications if you want more details. The clouds, the oceans, the eddies in the oceans all influence the climate and give a lot more sort of clarity as to what's going on. And so the big game that a lot of people are doing. There's some folks at MIT and and many, many other teams around the world are trying to capture all of those details, and they're trying to do it on grids. They try to turn the Earth into a grid with just a few miles apart if they can, and so these become much more complicated differential equations, and we'll see a little bit more of that in the next couple of lectures. But I do want to stress that the basic big picture of what's going on is more or less contained in this lecture, right? And so, and again, I think everybody should get to know a little bit about this. I don't think you should be a specialist to see how these things work. All right, that's the end of my lecture today, and we'll see everybody again on Wednesday at 1 o'clock Eastern, 1:05 Eastern.